Let me begin by thanking the organizers for the invitation to give the talk. I wish everyone present a happy new year. So this basically joint talk with Arjit there, Jyoti Dasgupta, Yas Khan, Umayna Khodda. Okay, so let M be a complex manifold. It's a complexly group, connected complexly group. H over M, a holomorphic principal H bundle. So let me quickly recall the definition. This is P is surjective holomorphic. No, I should first say EH is a complex manifold. E is holomorphic, surjective, submersion, H acts holomorphically. On H, that means this map. Action map is holomorphic. You can, from EH cross S2, you can project it to first EH, and then using P, you can go to M. And from here, EH, you can go to M. Identity map. Diagram commutes. Action is free and transitive on the fibers. Fibers of this can be written expressed in a much shorter way, but I tried to give the detail. Okay. So you have this. Now let us recall the construction of the Atiyah bundle and the Atiyah bundle and the Atiyah exact sequence. So you have the map P. You have the differential of P. Holomorphic tangent bundle of PH. The differential of E goes to P upper star of Tm. It is surjective because the map is a submersion. And the kernel is the vertical, along the orbits. The action is free, so it is, you can identify the kernel with the. Let us H, call it the Lie algebra of H. You get a short exact sequence given by the differential of the map P. Now the H acts on the action of EH, of course, produces action of H on tangent bundle. This preserves the vertical, of course. And so we can take the quotient by action of H on both sides, on all the terms. So here you get what you call the adjoint bundle. It's more or less a definition of the adjoint bundle. Alternative description is that a bundle associated to EH or the action of adjoint action of H on its Lie algebra. The vector bundle on it. This quotient is called the Atiyah bundle. And if you this option, if you take the quotient, of course, you get back the this is called the Atiyah bundle. This one. And this exact sequence called the Atiyah exact sequence. Definition of a holomorphic connection. Let me call DP, let us call it, this will produce a map here. Definition. A holomorphic connection on EH is a holomorphic splitting of the Atiyah exact sequence. That means a holomorphic homomorphism delta from Tm Atiyah EH such that first you apply delta and then you produce a composite F equal to identity map of the definition of holomorphic connection. Now, I will quickly recall the definition of curvature of a holomorphic connection. Before I recall the definition of curvature, first recall that the sheaf of tangent vectors, vector fields, sheaf of vector fields as a natural operation of Lie bracket. It is not a, remember that it is not all linear, the function will not come out of the bracket, but they have this Leibniz rule. So the Lie bracket operation of the vector field is invariant under the action, equivariant, sorry, I should not say invariant, it's equivariant for the action of H on the tangent bundle. So therefore, this sheaf of sections of this get structure of Lie algebra. Now this map being a differential of a map, Lie algebra structure preserving. This also is a Lie algebra structure because tangent bundle of M, sheaf of say, whole vector fields on M has a Lie algebra structure. So pullback we also have a Lie algebra structure. This map is Lie algebra structure preserving. So all maps are Lie algebra structure. This is the sorry. This is the this quotient. Sorry. So let me write it down. This is definition to be TEH. I didn't write that. Sorry. Quotiented by H. Sorry. Maybe I should say. I should have said. Tangent bundle of EH over EH. H acts on this and this equivalently. So you go about TEH. Sorry. This is M. Now this gives a projection and this makes a vector bundle. This is my Atiyah definition. Sorry. This is the definition of Atiyah bundle. Yeah. It's a very strong conditions. For example, I let me one quick. For example, M is scalar. In that case, all Chern classes has to vanish. Rational Chern classes has to vanish. They're very strong condition. Fairly, yeah. For the Riemann surface, there is another theorem. Since you asked the question, a holomorphic vector bundle on a theorem of Well and Andrei and Atiyah says that a holomorphic vector bundle on a compact Riemann surface admits if and only if every direct summand of is of degree 0. Every vector bundle you can write it as a direct sum of indecomposable vector bundles. That's very obvious. You can keep breaking it. If it is admits a holomorphic connection, if and only if the indecomposable, in particular, indecomposable vector bundle on a Riemann surface admits a compact Riemann admits a holomorphic connection if and only if degree is 0. It is a condition, but it's not. Yeah, I don't know how to call it, too strong or not so strong. The degree condition is of course a serious condition. The degree is 0. Okay. Okay, so let me repeat it again then, since I have defined it. The ATIA, a holomorphic connection is a splitting of this exact sequence. This exact sequence is obtained by just taking quotient by H, all the terms. And the connection is a splitting of this. So next I said that every term has Lie algebra structure. So now we have a homomorphism like this. So you suppose you have vector fields V and W, vector fields, sections of locally defined vector field. I'm writing T of M, but I'm not demanding a globally defined vector field. Suppose take in the part of the sheaf, gamma, you think about the sheaf. That means locally defined holomorphic vector field. Suppose you have a connection like this, delta. So now you can take delta of V, delta of W, Lie bracket. Now subtract delta of send VW to V, W. This. Now, since it's a splitting, when you home is splitting, when you a priori it is a section of ATIEH. But if you project it to T of M, this section by this map, I call it F, then you get 0. Because all the homomorphisms are Lie algebra structure preserving. F is Lie algebra structure preserving, and delta is a splitting homomorphism. So composition is identity. So you can easily check. It requires a little bit checking, but very simple check, straightforward check that this is 0. This goes to 0. So this is a section of the kernel, namely IDEH. This is a section of now more. This part is, but the interesting part is that this now becomes linear, Ox linear. Namely, if you multiply F by a function V vector V by a suppose a vector field by a function, say gamma, infinity holomorphic function. If you put gamma, maybe I should not put here. If you replace put gamma here by the Leibniz rule, what extra term comes out? W acting on gamma times V. That vector field comes out by the Leibniz rule. And on the other factor also, because this Lie bracket was obtained by the Lie bracket of vector field. So same thing, same object comes out. So and they cancel off. The final outcome becomes delta of gamma V, delta of W bracket minus delta of gamma V comma W is simply gamma times delta V delta W minus delta of When you take Lie bracket, let me repeat it again. When you take Lie bracket, multiply vector field, the function doesn't come out. But here, in this case, it comes out because. But the nonlinear, that extra term that cancel off. Anyway, so that means it's a. What does it imply? It implies that it is a map of vector bundles. This operation is not a map of sheaves, but map of vector bundles. It is given by fiber-wise map. In particular, you get a holomorphic section of this, which is called the curvature. And the connection delta is called flat or integrable if the curvature is 0. A section of this, which is identically 0, then you call curvature. So yeah. Suppose E inside M is a normal crossing divisor. Namely, locally it's like coordinates meeting. So factors are transversal components. A technical condition on the singularity. So now suppose then you have this logarithmic tangent bundle. Recall if the tangent bundle of M, you can restrict the tangent bundle to the vector bundle to D. Now then you quotient it to Tm, restricted to T, tangent bundle of D. Look at the composition. The kernel of this composition is called Tm minus log D. Logarithmic tangent model. Now, what I can do is that first note that E from EH to M was a submersion. So if I take the normal crossing divisor, so P inverse of D, this is also a normal crossing divisor. So now I can make some small changes. Here I can minus log D. Here it will become minus log dP, P inverse of D. I should rewrite separately, but so now again I take the quotient. So then we get the other logarithmic Atiyah exact sequence. I keep the definition here. I don't want to temper the definition. So yeah, this is good one. So this minus log E inverse D to EH minus log P inverse D, and this is called Atiyah minus log D. This quotient. So I get a different vector bundle which is called logarithmic Atiyah bundle. It is called the logarithmic Atiyah bundle. Just before the instead of Tm, I take Tm minus log D, and I take the inverse image. I also have to take the appropriate modify the tangent model. So that is you get the logarithmic Atiyah exact sequence. Logarithmic connection on EH is a holomorphic splitting of the logarithmic. Atiyah exact sequence. That means minus log D. That the composition is identity on minus. The same definition, same everything is same, but just you can replace by log D. So this. No, in a normal crossing device is smooth. I have to take smooth. Otherwise, minus log D is log D is defining is messy. Because I took the kernel, right? Yeah, it is not D. Sorry, where is the define? Yeah. That's a little problem to get a vector bundle. You will not get a vector bundle. You will get a sheaf. Okay, so what was the question? Components are smooth or components are smooth. I mean, only it's a normal crossing divisor. Components are smooth. Locally, it is a smooth, intersecting normally. No, yeah. Let me, yeah. So now, yeah, so just 1 second, one more statement. Just as defined, curvature was defined, you can logarithmic connection, you can define the curvature. The only thing is that it goes to omega 2 minus log, it is omega 2 m plus log d. Omega 2 log d. This section of omega 2 log d. Adjournment. Curvature is a section of that. Anyway. Now, suppose G is a complex Lie group. Acting holomorphically on N. So you have G cross M, the action map is holomorphic. Now we have the tangent space level map. So tangent bundle of G cross M, tangent bundle of M. So on the other hand, you G cross M contains identity cross M. You can restrict this tangent bundle to that. And the tangent bundle splits into, the product of course splits into tangent bundle of G and tangent bundle of M. You throw away the tangent bundle of M and only take the tangent bundle of G. So finally you get a map from M cross the real algebra of G, which will denote by G. M cross G to tangent bundle of M. First writing restricting to identity cross M and then taking the component of the tangent bundle in the direction of the subbundle. And then you get a map. So now once you have this map, let's call it a name, again give a name beta given by the action. We can modify the Atiyah exact sequence. This is a beta map. Now I can pull back the exact sequence. That means I take the direct sum of these and take the subspace, subsheaf of that which goes where the two maps coincide. That is denoted by Atiyah. This consists of all V, W, namely Atiyah over some point M, and here M cross G, such that F of V is equal to beta of W. This is the definition, and this map is the projecting to the first factor. This is the identity map, this is the beta. So this will be used. So let me, I can now state or state this. What is that? So we for criteria for a bundle to be homogeneous. So recall that EH is a bundle on M and G is acting on M. So asking EH is called homogeneous. EH definition, EH is called homogeneous if for any element of G, the G is acting on M. So I'll for any element, what did I write? G is acting on. Anyway, for any element of G, I'll denote by rho G the action of M. The action of G on M. A is called homogeneous if rho G upper star of EH is equal to EH, isomorphic to EH for all G. And it will be called equivariant if the action of G leads to EH such that the actions of which lives and commutes with the action of H. So let me write the proposition. EH is homogeneous if and only if this exact sequence star has a holomorphic splitting, admits a holomorphic splitting. Second, another proposition. Assume G simply connected. I'll first state and then explain. EH admits an equivariant structure see, of course, I mention, I don't know. Of course, the equivariant implies homogeneous because the action leaves. So, of course, for each element, they'll become automatically, using the action, they are become isomorphic. So, this is stronger condition that the action leaves than actually pullbacks are isomorphic. So of course, equivariant implies homogeneous. Assume that the G is simply connected. Then EH admits an equivariant structure if and only if the star has integrable or flat splitting. Yeah, since I didn't, I'm running behind it. I didn't explain it well. See, just as you, from the connection, recall the holomorphic connection was a holomorphic splitting, and from that you can define the curvature. So here also from the holomorphic splitting you can define the analog of curvature. So this becomes a section of add EH tensor lambda 2 G star. This is we use the same definition of curvature, because you take any two sections and then take the image and then take the image of the two sections and then take the Lie bracket, because the bracket operation is there, and then or in the take the bracket itself and take the image and take the difference. That becomes a section like just as curvature, the same construction of curvature, same identical construction of curvature, the section of this. So here it says that if it admits a holomorphic splitting like a holomorphic connection analog, and it has a equivariant, which is stronger condition, for that you require the curvature to be 0. Okay, now we come to toric. Now suppose M is toric, M comma G, G was acting on M, so this is toric. Good. That means G is product of GM, multiplicative with C star, it is product of that. And it is acting on M. Toric means that it has a open dense orbit on which the action is free. Toric, smooth toric. I'm not considering a smooth case, so it's toric. M, G is a product of multiplicative group GM, C star, copies of C star. G is a copies of C star. M has a open dense G orbit on which the action is free. Now we have a divisor D on M, but the action is not free. But the action is not free. My M is a manifold, so this means D is a normal crossing divisor. The normal crossing divisor. In that case, this map beta, image of beta, is Tm minus log. So I deleted many things. So if you compare the construction of the RTI exact sequence, logarithmic RTI exact sequence, and then we constructed this, this is becoming the logarithmic tangent bundle. So this is becoming the logarithmic RTI exact sequence. So splitting is just a logarithmic connection, right? Because this. Then this just simply becomes the logarithmic RTI exact sequence, and this becomes a logarithmic tangent bundle. So this says in the toric case, G is homogeneous if and only if this has a holomorphic splitting. So this now becomes whether if and only if the logarithmic tangent bundle has a holomorphic splitting. And we recall that the definition of logarithmic connection is a holomorphic splitting of the logarithmic tangent bundle, right? Logarithmic RTI exact sequence. So the corollary is as follows. Corollary. In the toric case, corollary, EH is homogeneous if and only if it admits logarithmic connection. Singular locus is contained in the D. Singular locus contained in D. This is a corollary. So I can also formulate this, but this becomes, in the toric case, becomes much. Now I'll state a theorem. You noted that equivariant is a stronger condition, right, than homogeneity, the way what you define. So we say that if and only if a logarithmic connection, then it is homogeneous. But I have to say that it is. I have to make an assumption. Theorem. E reductive. No, sorry, H reductive. The same way I was saying. Then EH is equivariant if and only if it admits a logarithmic connection. Note that in the earlier case, you need simply connectedness, and then you needed, for equivariant, you needed a flat connection. But here, this is just directly getting strengthened. You don't need any flatness condition. That what is required for homogeneity, that is enough. That means any homogeneous bundle admits equivariance. Okay. So we had, for example, some on this topic. For example, Kliasko had a classification of equivariant bundles, equivariant vector bundles, and toric varieties. That program can be that his classification can be generalized to principal bundles when principal H bundles where H is reactive on a smooth toric variety. So he had a classification of holomorphic vector bundle, equivariant vector bundle on smooth toric, and then you have the corresponding thing for classification for, you could do that for smooth toric, but instead of vector bundle, take principal bundle is reactive to the structure. Okay, but let me not get into that. So I wanted a few things, stability. Let me see if I can manage to. Actually, let me reverse that. I wanted to state a result about stable equivariant bundle, and then make a statement in the proof of that what one of the crucial ingredients goes into the proof. So I'll reverse that. I'll just first state a proposition which is used in the theorem on equivariant bundle. So, because I may not have time to first those. I'm just because that other result is I guess it's of independent interest, but it was mainly came to use in the proof of the theorem on stable bundles, stable principal bundles. Okay, so now let me. So now, suppose H is again reductive algebraic group and complex, everything about complex, and suppose L is a Levy subgroup of some parabolic subgroup. of a parabolic subgroup. Subgroup of H. EH over M. M is toric. EH over M and equivariant principal H bundle. Equivalent for the toric action. Toric, the group G is acting and this is equivariant. The action leaves the commutes G and H action. Question. When does E H admit an equivariant reduction of structure group to L, to the Levy subgroup. I have a G bundle, equivariant bundle. I have a subgroup of the group H. I want to ask when the principal bundle can be admit a reduction of structure group. Not only that reduction of structure group, it should be equivariant reduction of structure group. The reduction should be equivariant and is preserved by the action of EH. Recall reduction of structure group means I have to produce EL inside EH. H acts freely transitively on the fiber, the action of on the fibers. The action of now consider the action of L. L is a subgroup. EL is first preserved by the action, and on the fibers of this L is transitive. The action of L is transitive. EL is preserved by the action of L, and the action is transitive. So that's a reduction of structure. Now consider automorphisms of. First consider holomorphic automorphism of EH of the fiber bundle, principal bundle, or the identity map of M, and then you consider all automorphisms which commute with the action of G. So now this has a map to this is contained in H, not canonically, but up to conjugation. Because automorphism is a section of the gauge bundle, and it is you can evaluate the section, and the fibers of the gauge bundle are identified with the group itself. So it is contained in that. The answer: admission reduction. Yes, if this subgroup contains a conjugate of the center of L. If and only if. Reduction admits the equivalent reduction if and only if this group contains a conjugate of the center of L. I think my time is up, so I stop with the application without. Thank you for your attention.